Chapter 11, Goodness of Fit and Contingency Tables. Hypothesis test and confidence interval for unknown population standard deviation. Have used the chi-square distribution to make a decision in the test of independence and test of goodness of fit. We compare observed data to what the data would be expected to look like if the null hypothesis is true. Test statistics measures the difference between observed and expected data. If the difference are large, the observed and expected data are different, then observed data contradicts the null hypothesis. If the difference are small, then the observed and expected data are similar, then the observed data does not contradict the null hypothesis. The test statistics measures the difference between observed and expected data, so we follow the chi-square distribution. There's going to be two cases. Case one is where observed and expected data are different. That means the difference is large, so the test statistic is going to be large. So it's going to be far out in the right tail of the chi-square distribution, which means the p-value is going to be small, as you can see in the graph. Case two is where the observed and expected data are similar, so the difference is going to be small. So the test statistics is going to be small, which means it's going to be close to zero. So it's going to be to the right, far right to the right of the distribution. So the p-value or the area under the graph is going to be larger, as you can see. So starting with chi-square goodness of fit, writing the hypothesis test for a goodness of fit test, null hypothesis states a probability distribution that we think the population follows. We look at the sample data to decide if the population follows the distribution or not, and then we write the hypothesis. In the null, we say that the data fits the expected distribution. In the alternate, we say that the data does not fit the expected distribution. We decide using significance level alpha, and then we find the test statistics p-value. We draw the graph and the conclusion. We compare the p-value to significance level to make a decision, and we write a conclusion. So let's start with the first example, chi-square goodness of fit test. The table below shows the age distribution of Facebook users. The age distribution of Facebook users in 2012. So it's giving you the age range and the percentage. So it's showing you that 7% are between the ages 0 to 17, 9% are between the ages 18 to 24, 19% are between the ages 25 and 34, and so on. Suppose a random sample of 175 Twitter users has the age distribution below. So the next table shows you the age distribution for a sample of 175 Twitter users. So it's telling you that 14 of them are between the ages 0 to 17, 25 of the 175 is between 18 to 24, and so on. So we want to know if the age distribution of Twitter users fits the same age distribution as Facebook users. What would the sample data look like if they exactly follow the expected distribution? So the expected distribution in this case is Facebook. We want to see if Twitter users fits the same age distribution as Facebook users. So that would be the null hypothesis. So in the null, I'm going to say that the age distribution of Twitter users fits the same age distribution as Facebook users. And then in the alternate, I'm going to say that age distribution of Twitter users does not fit the same age distribution as Facebook users. So I have the categories, the ages, and the observed data, it's what's given to you. It's the 175 Twitter users. that are 14 are between the ages 0 to 17, 25 are between 18 to 24, 39 are between 25 and 34, and so on. So 41, 40, 11, and 5. The expected distribution is the Facebook distribution, which says that 7% are between 0 to 17. So if it follows the same distribution, if Twitter users follows the same age distribution as Facebook, then from the 175 users, 7% of them, so you're going to find 7% of 175, 7% of them should be between the ages 0 to 17, which gives us 12.25. So from the 175, 9% should be between the ages 18 to 24, so that's about 15.75 people. From the 175, 19%, so you find 19% of 175, which is 33.25. From the 175, 20% should be between the ages 35 and 44, so that's about 35 people. 175 times 0.33, which gives me 57.75. From 175, 9% again are between the ages 55 and 64. That's about 15.75. And 175, 3% are 65 and over. So that's about 5.25. Okay, so now using StatCrunch to do this, you want to go on Stat, make sure you enter the data. You go on Stat. From there, we're going to go on Goodness of Fit. So Goodness of Fit test. And from there, you want to go on chi-square distribution, chi-square test. Okay, so let's go on StatCrunch. I did already entered my observed and expected data. So from here, we go into Stat, Goodness of Fit, chi-square test. Observed is in the observed column, and I already named them observed. And then the expected is in the expected column, and then we compute. So it gives me 6 degrees of freedom. So it's categories -1. There's the chi-square value, which is 14.6055. And it also gives you the p-value, which is 0.0236. Okay, so let's go back and write down what we got. And you always want to show the graph. So it's based on a chi-square distribution. So based on a chi-square distribution, which is always skewed to the right. So it looks something like this. Since the area is about 0.0236, then that means it's a small area right here. That's our p-value, which is about 0.0236, and it's a chi-square value. So number of cells, there's 1, 2, 3, 4, 5, 6, 7 categories. 7 minus 1 gives us 6 degrees of freedom. P-value is 0.0236. The chi-square value is 14.6055. Yeah, this is our p-value. So decision, we're going to reject the null. And the reason for that is since our p-value, which is 0.0236, this is smaller than alpha significance level. So that's the reason. So if you're rejecting the null, then at 5% level of significance, the sample data provided sufficient evidence to conclude that the age distribution of Twitter users is different from the age distribution of Facebook users. So that means the age distribution of Twitter users does not fit the same age distribution as Facebook users. You can also say there is sufficient evidence to reject the claim, since the claim is to see if they're the same, to reject the claim that the age distribution of Twitter users fits the same age distribution as Facebook users. So this is how you write a conclusion. Let's move on to the next example. Okay, next example, hypothesis test for goodness of fit. So are births uniformly distributed by the day of the week? The health official wants to know whether the births in the country are uniformly in the county are uniformly distributed by the day of the week. A sample of 434 randomly selected births at a hospital in a county are given to you. So they're given to you by day of the week: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So 41 babies are born on Sunday, 64 are born on Monday, 71 on Tuesday, 72 on Wednesday, and so on, using 0.05 significance level. So we're gonna write, so we're looking at a uniform distribution, and you're gonna see this also in the homework. So we're gonna say that births in the county fits the uniform distribution, or you can say they are uniformly distributed by the day of the week, or they're not uniformly distributed. So I'm going to say that you can say, again, births are going to fit the uniform distribution, or we can say births are uniformly distributed by day of week, or an alternate, we say that births are not uniformly distributed by day of week. Okay, so the observed data, it's given to us. So it's saying that 41 babies are born on Sunday, 64 on Monday, 71 on Tuesday, 72 on Wednesday, 71 on Thursday, 69 on Friday, and 46 are on Saturday. Now, if they're uniformly distributed, that means equally likely. So you take the total, which is 434, and you divide it by 7 days of the week, which gives us 62. So that means 62 babies are going to be born each day if it's uniformly distributed, if it fits the uniform distribution. So let's go on StatCrunch. You're gonna have to go on StatCrunch and do goodness of fit test, and I already have the observed data. In the expected, you can also put 62 for each data value, or actually StatCrunch does this for you. So you go into Stat goodness of fit, chi-square, and observed is in the observed. If you enter the expected data as 62 each, then you select that, or you can say that all cells are equal proportion. So it takes the total and divides it by 7 categories, and you compute. So there's the expected, then there's the observed data. Your chi-square value is 16.3226. Your p-value is 0.0121. Okay, so let's go back and write down what we got. So it's a chi-square distribution, so it's always going to be skewed to the right. It's a small area in the right tail. So p-value, it's about 0.0121. That's the area. This is chi-square. So we have 7 categories, 7 days of the week, -1 gives us 6 degrees of freedom. P-value is 0.0121 with 6 degrees of freedom. Chi-square is 16 point, that's our test statistic, 3226. Okay, so then we're gonna have to now make a decision. So the decision is to reject the null. So again, I'm rejecting the null because my p-value, which is 0.0121, is smaller than alpha. So at 5% level of significance, the sample data provides sufficient evidence to reject the claim, since the claim is, we're testing the claim to see if they're uniformly distributed. To reject the claim that births in the county are uniformly distributed by the day of the week. Okay, moving on to the next part, contingency table, or a two-way frequency table, is a table consisting frequency counts of categorical data of 2 different variables. One variable is used for category for the rows, and the second variable is used to label the columns. So that's when the chi-square test for independence comes in. So we use the hypothesis test for independence to help us decide whether two variables are independent or not. So in the null hypothesis assumes that the variables are independent. In alternate, we always challenge that and we say they're not independent. So then we also calculate the expected data, and then we compare expected and observed kind of the same way. And then we write our hypotheses. So in the null, you're always going to say that the variables, and you're going to have to describe what the variables are, that they are independent. In the alternate, we say that the variables are not independent. And then from there, we do our test, and then we find the test statistic p-value, we make a decision, and we write a conclusion. Okay, so here is the first example for hypothesis test for independence. Okay, so this example, hypothesis test for independence, a professor believes that giving extra time on an exam won't affect the grades. He divided a random sample of 300 students into two groups and gave the same test. The first group had 1 hour to complete the exam. The second group had unlimited time. At 5% level of significance, is there sample evidence to show time on exam and grades are related? So here's the data. Students got A, B, C, and Fs. So people that had 1 hour, these are their grades. 23 got A's, 42 got B's, and so on. And people who had unlimited time, 17 of them got A's, 48 got B's, 85 got C, and 8 got F. So null hypotheses, we assume that they are independent. So we're gonna say grade and time are independent. In alternate, we say that grade and time are dependent or not independent. So degrees of freedom, it's the number of rows minus 1, number of columns minus 1. So 2 minus 1, 4 minus 1 gives us 3. And then, so to do the next part, we're going to have to use StatCrunch to do the next part. So we go into StatCrunch, and I already entered my A, B, C, F. I already entered everything, what they got. So from here, this is a two-way table. So you want to go into Stat. We go into tables. So you want to go on table and go on, let's do this again. We go on table, go on contingency. With summary. Okay, with summary, make sure you select all the columns. So we want to select all of these. All these are the columns. So Control A, we select all, and then row label. It could be any of them. It doesn't really matter what you label. And then display, make sure if you want to see the expected count, click on here and then we compute. So there it is. What's in the parentheses is the expected data. And then the other one is your data. There down here, you have the chi-square value, which is 3.9245. And then there's the p-value 0.2697. Okay, so let's go back and write down what we got. So the chi-square, we got 3.9245. And the p-value is 0.2697, which there's the graph. It's a chi-square distribution. That's the area. And I said, do not reject the null because my p-value is greater than significance level. So at 5% level of significance, the data does not show enough evidence to show that the allowed time for exam and grade earned on the exam are dependent. So we believe that they are independent. Okay, so let's look at one more example. This is hypothesis test for homogeneity. So according to Yale Daily News, okay, so next example, hypothesis test for homogeneity. According to Yale Daily News, the acceptance rate for incoming freshmen who applied to league schools are reaching record lows. So looking at the count of number of students who were accepted or denied are given to Yale, Columbia, or Princeton are summarized. We want to calculate the proportion of applicants accepted at each of these schools. Is there evidence to suggest that the proportion of applicants accepted to Yale, Columbia, and Princeton are not equal? So these are given to you. So this is called homogeneity because we're comparing proportion more than two proportions. So I'm going to let P1 be the proportion of accepted at Yale, P2 be the proportion of accepted at Columbia, and P3 be the proportion of accepted at Princeton. So we're going to say in the null that they are equal, proportion of expected at all three schools are equal. In the alternate, we're going to say that at least one school has a different proportion of accepted. So that means they're not equal. So this is still two-way tables, contingency tables. So if you go into StatCrunch, you're gonna have to do the same thing. We enter the data. I did already for Yale, Columbia, Princeton. I go into stat and I go into tables, contingency with summary, and I have to select all the columns. Row label doesn't matter, it could be any of these. And then if you want to see the expected count, you can click on expected count and then we click compute. So there's these are your data values. What's in the parentheses, it's the expected data. Degrees of freedom is 2. Your chi-square value, it's 10.7320. P-value is 0.0047. So let's write down what we have. So the chi-square value, I got 10.7320. P-value is 0.0047. And you can do a graph. You can show the graph. It's a chi-square distribution. A very small area in the tail is going to be shaded because the p-value is 0.0047, which is really small. So let's now make a decision. So the decision is to reject the null hypotheses. And the reason for that is because 0.0047, this is smaller than significance level in this problem, which was 0.01. So at 5% level of significance, there is sufficient evidence to support the claim that the proportion of applicants accepted to Yale, Columbia, and Princeton are not all equal. So that's the end of this section.